Hello everybody, my name is Oliver Marquardt from Weierstrass Institute for Applied Analysis and Stochastics in Berlin. And today I'll be talking about nucleation chronology and electronic properties of indium arsenide antimonide phosphide graded composition quantum dots. This work has been done in collaboration with Karin Gambaryan from Yerevan State University in Armenia, who has visited our institute about a year ago, Thorsten Bück from Institute for Crystal Growth in Berlin, and Achim Trampert from Paul Rude Institute for Solid State Electronics in Berlin. Well, why are we interested in indium arsenide antimonide phosphide and in particular on nanostructures grown from this material? Well, indium arsenide antimonide phosphide grants you a well-defined access to the mid-infrared spectrum by modifying the antimonide and phosphide content. Applications of this would be thermal or generally infrared detectors, gas sensing, photoresistors, photoconductive cells for solar energy harvesting, and so on. And the systems I am talking about today have been grown using liquid phase epitaxy, which is a robust and inexpensive approach to produce semiconductor heterostructures in a surprisingly good crystal quality. A particular strength of the liquid phase epitaxy is that one can introduce on purpose a compositional grading, so you can introduce a composition gradient within your heterostructure, which is very useful to significantly improve the crystal quality, in particular in material systems that exhibit a large lattice mismatch. We have also seen in the past that nanostructures such as quantum dots, quantum rings, quantum dot molecules even, can be grown in a controlled manner using the liquid phase epitaxy. So the indium arsenide antimonide phosphide graded composition quantum dots that we are talking about here have been grown from the liquid phase of indium arsenide antimony and phosphorus at 540 degrees C at Yerevan State University, and they were grown on undoped commercial indium arsenide substrate by my colleague Karin. There was a 2% intentional lattice mismatch which has been controlled by the antimonide and phosphide content present in the initial liquid. And a specific of our growth process is that the growth temperature was kept constant while supersaturation of the liquid phase was controlled by the composition of the liquid according to the phase diagram. In particular, I'd like to stress out that characteristic parameters of heterostructures, for instance diameters or heights of quantum dots, can be controlled to a certain extent in a well-defined manner using this growth process. So our samples have been characterized using atomic force microscopy and scanning tunneling electron microscopy by our colleagues at Institute for Crystal Growth Berlin and Paul Rude Institute Berlin. We have seen first of all that our graded composition quantum dots exhibit an average diameter of 75 nanometers and an average height of 8 nanometers. The surface density was estimated to be 3 to 7 times 10 to the 9 per square centimeter, and it would be typical for LPE grown systems to see the maximum of an antimonide content at the top of the systems, which we estimate here from strain profiles and composition of the original initial liquid to be about 20%, and the maximum phosphorus content of 15% at the bottom of the system, and both decrease to zero at the for the antimonide content at the bottom of the system and for the phosphorus content at the top. And we assume that our graded composition quantum dots have a conical or lens shape. We are not completely sure about that. The optical properties of our systems were characterized in Armenia using Fourier transform infrared spectroscopy. Measurements were done at 283 Kelvin. What we see is an absorption of the graded composition quantum dots at 3.83 microns, whereas the indium arsenide substrate as a reference has the expected 3.47 microns. Also, there is a peak observed in the reference indium arsenide substrate, which is missing in the graded composition sample, graded composition quantum dot sample. And the reason for this missing peak is certainly that the surface properties of the system with the graded composition quantum dots is of course significantly modified. Also the surface resistance of the sample with the graded composition quantum dots is about 3 times larger than the one of the indium arsenide substrate reference, so this points towards the same direction. We have then performed some simulations to shed more light on the electronic properties of these systems. The formalisms we use here are continuum models. First of all, we have computed the strain distribution using continuum elasticity theory, and this enters then, together with much more parameters, the simulation of the electronic properties using an 8-band K.P model for zinc blende crystals. Both formalisms were implemented within the plane wave framework of the Swings software library. Let me mention that the system we are talking about is a type 2 heterostructures. The holes can be expected to be confined somewhere in the graded composition quantum dots, whereas the electrons will be in the indium arsenide substrate on a continuum energy level. So only the whole states, or even the whole ground state, was of interest here for us. All relevant input parameters were taken from Vogelman's paper, which is pretty much the standard for such simulations. And as these parameters are designed for 0K calculations, we had to correct the energies to 283 Kelvin using Varshny's correction. This shows you the workflow of such a simulation. So first of all, you start by defining the geometry and the composition of your heterostructure in a 3D material map, which is pretty much a simple ASCII file. Next, you define the parameters of all materials involved, which for the first step would be lattice, elastic, and piezoelectric constants, and later on effective masses, band offsets, and band couplings for the electronic properties. In the next step, we run a continuum elasticity module, which gives us the strain distribution in the system. And for the sake of completeness, let me mention that there's also a Poisson solver which computes from strain and piezoelectric constants the built-in electrostatic potentials. Here in this particular case, these are very, very small. So yes, we have them in the simulation, but they contribute only like about single MeV's energy difference to the bands, and they have their extrema at the outer corners of our system, so they really don't play a role here. In the next step, we run an eigenvalue solver using a multiband, here in this particular case the 8-band K.P Hamiltonian. Let me mention that we are not limited to the 8-band model, so we can essentially plug in any Hamiltonian we like, and this gives us single particle electronic properties, so eigenvalues and wave functions and charge densities. It is generally possible to run a self-consistency loop here at that point, which would give you information on the excitonic part, but given that we have a type 2 system here, we neglected the excitonic interaction because it's extremely small. Please let me advertise at this point that there is a software tutorial in the context of the NUSOT, which has been made available on the Swings repository website, as you can see here. So let's have a look at the elastic properties of the system. What you see on the left side are hydrostatic and biaxial strains, and both of them exhibit a maximum of about 1%. For the hydrostatic, clearly at the top of the cones, which is not too surprising, first of all, because, well, it's the top of a cone, so of course elastic relaxation is strongest there. And second, it has the maximum antimonide content. And for the biaxial strain, we see maxima also at the top, but also on the very bottom where the phosphide content is largest. On the right side, you see the band structures. The dashed lines are the ones unmodified by strain, so only from the bulk parameters. And the solid ones are the ones that see modifications from strain and deformation potentials. And what you see here is first, if you look at this plot, you see the conduction band, the red line, which has a minimum on the left side. The left side here of this plot is essentially the indium arsenide substrate. And then the band throughout the quantum dot is pretty much flat due to modifications from strain. And for the valence band, you see that the maximum of the valence band is pretty much at the tip of the quantum dot, and modifications due to strain are very, very small, so which gives us then a type 2 heterostructure with the electrons being somewhere in the indium arsenide substrate, and the hole here indicated as a black line will be somewhere in the tip of the graded composition quantum dot. Now for the electronic properties. The left side here shows you the transition energy of our systems for different graded composition quantum dot base radii and heights. So the radii are shown as numbers here to the respective lines, and the whole thing is plotted as a function of the height of the quantum dots. There's a typical quantum dot shown in the middle. The gray isosurfaces indicate the increasing antimonide content towards the tip of the graded composition quantum dots, and the blue area is the whole ground state in such a system. Next, we have mapped the energies from our simulations after applying a Varshny's correction for T equals 283 Kelvin, which makes about 60 MeV, to the diameter distribution we have seen in experiments. So that's essentially the gray bar you see here on the left side gives you the systems that were observed in experiment, and we have then mapped this on the corresponding histogram and produced something like a simulated spectrum. And we were really surprised to see that the simulated peak is extremely close to the one observed in the experiment. So that really surprised us, because we have essentially taken the formalism out of the box, plugged it into our software. We have taken the parameters from Rogaftman just as they were without any modification, and then applied the Varshny correction on top of that. That's everything that entered, and still the agreement is extremely good, and we think it's a well-suited approach for a theory-guided design. So of course we cannot tell experimentalists to grow extremely specific systems here with one very well-defined diameter or height, but we can point the direction what to do with their systems if they want to address a certain spectral window in mid-infrared. So let me summarize my presentation. I have been talking about indium arsenide antimonide phosphide graded composition quantum dots today that were grown using liquid phase epitaxy. The average diameter of our systems was observed to be 75 nanometers with average heights of 8 nanometers, and we have simulated absorption spectra using continuum elasticity and 8-band K.P model, and then mapped these energies after applying a Varshny correction on the diameter distribution observed in experiment. We found an excellent match with experimentally observed spectra, and that allows us to conclude that we can use this approach for a theory-guided design to help experimentalists to look for specific systems. I would like to acknowledge funding for Karen visiting Germany last year by Deutscher Akademischer Austauschdienst, DAAD, German Academic Exchange Service, and I personally acknowledge funding by the Deutsche Forschungsgemeinschaft DFG, German Research Foundation, under Germany's Excellence Strategy MAT Plus Berlin Mathematics Research Center with project number AA2/5. And of course, I would like to thank you for your attention.